Okay, so let's begin. Welcome back to our lectures on the fundamentals of Aerosecond Science and Technology, which we bring to you from IIT Madras and IIT Tirupati. We are now in the third module and the second lecture of this module, which we call nonlinear optics in a nutshell. Okay, so it's indeed in a nutshell, pretty compact, I would say. That's very intentional because this course is has a broader goal or a larger goal in some sense. So, we will want to march towards that as quickly, but after some efficient communication of core principles of this subject. So, in addition to the books that I have been flashing earlier, I have included a very nice, I would say iconic text for both learners and practitioners of photonic science. When it comes to nonlinear optics, the textbook by it's R. Boyd. I have recognized a typo, but he's called Bob Boyd, so I probably made it B. Robert Boyd's book, Nonlinear Optics, is really a treasure. And I would also like to recommend you to listen to his lectures, which are available on YouTube. Although in that case, if my memory serves me right, one could have wished for better video and audio quality. Ours is, I am sure, in this case much better. But credits to Professor Trebino as always for his immense inputs and contributions to our present endeavor. So, I am not going to do a lengthy recap, but let me give you a sort of timeline of what brought us on to this nonlinear optics primer or nonlinear optics in a nutshell. It is our discussions of pulses in the time and frequency domain and the phase terms, chirp and so on, as well as concepts about the propagation of pulses, how to deal with propagation, because a pulse is never stationary, although we use a co-moving frame or frame of reference that runs along with the pulse, and also make our orient ourselves towards pulse metrology in the time domain. These are very important salient features of optical pulses, and also in this case what is going to come into our ambit as attosecond pulses. And for all this, a foray into nonlinear optics is absolutely essential. We just cannot escape this, sidestep this, look over this or bypass this. So, let us do a quick recap of optical light pulses, which look like that, and we looked at their propagation in the previous class, where we understood that the pulse traveling through a medium could undergo refractive changes in terms of the frequency dependent refractive index or absorptive change or deformation, whatever you like to call it, in which case a pulse that enters with even a very flat spectral phase denoted here by the dotted violet line and a very reasonable Gaussian like envelope, both depicted in the spectral domain, which is where we will very likely have measured the pulse. We have not yet discussed how to do it, we will discuss that. It goes through a medium and it undergoes some kind of, if you like, deformation. Evidently, in this cartoon, the width of the pulse, if you consider a full width at half max, has broadened, and the spectral phase has gone from sort of being flat, which is, you can say, is phi of omega being 0 throughout, to some non linear sort of quadratic or cubic kind of phase profile. That is the output. All of this is captured in writing the output in terms of the input as something multiplied by exponential factor minus alpha L by 2 times exponent I times n k times L. So, this is to say that the amplitude, the input amplitude function, spectral amplitude function, is modulated by the frequency dependent absorbance alpha in the exponent. So, it is quite a strong effect when you even if you have a numerically tiny bit of absorbance. Absorbance, of course, is defined through the Beer-Lambert law, where alpha is related to the logarithm of the ratio of the input to the output intensities, both of which are easily measured in a laboratory, L being the sample length, and this rest of it is the phase part. Now, we can look through all the details of pulse propagation and come to the conclusion that the output spectrum is the input spectrum multiplied by the exponential loss factor, and the output, the phase at the output of this propagation is the input phase plus, in this case not multiplicative, plus the n omega by c times L factor. Now, pulse length, we made a quick definition, but yet very efficient definition of pulse width as the effective width, where if I consider a pulse of no matter what shape, take the maximum of the amplitude, fix that, and then integrate the area under the curve. If the envelope here represents the intensity envelope, this would, the area under the curve would give us the energy, and then replace the pulse with an equivalent energetically equivalent rectangular pulse with an identical maximal amplitude and define a T effective by that. If we do that and represent a T effective by this means, we can we will arrive at a very nice relation between T effective in the temporal domain and delta W effective, if you wish, in the spectral domain. But we can consider a whole other, whole range of pulse width quantities which are measures of pulse width, the root mean square width, where we essentially multiply this with the square of f of t. If we had t multiplying this for symmetric pulses, this entire integral would have vanished. So, the second moment alone would sort of survive. So, this is delta t RMS, but then our most popular definition of pulse width is through the full width at half max, which is, the name speaks for itself, or the term speaks for itself as to what it is. Now, whatever means of width we consider, all these would obey a sort of uncertainty relation, where delta omega delta t, the product, is in this case at best 2 pi, and it only can be larger than this, or delta nu delta t can at best be 1 and is forced to be larger than this. Okay. So, the right hand sides would vary depending on various definitions. For every pulse that we encounter, we can define, therefore, using these widths in whichever form we define in the temporal and spectral domains delta t and delta nu respectively, a time bandwidth product TBP, which is a number. It is a dimensionless number because we are multiplying frequency and time, and this number is the least for what we would call a Fourier transform limited or simply a transform limited pulse, right. So, based on the shape of the pulse, whether it is Gauss, secant hyperbolic, Lorentz, or some asymmetric secant hyperbolic, or even the kind of rectangular pulse that we considered initially, and depending upon the definition of the width, which most popularly is full width at half max, the time bandwidth product for transform limited pulses can be written down. Transform limited pulses, as I told you, are pulses with a flat spectral phase essentially. Okay. The best or the neatest form of spectral phase profile that you have is flat, in which case they are best transform limited in the time and frequency domain correspondingly. In other words, the higher order phase coefficients phi 1, phi 2, phi 3 are all 0 identically in either domain, and we earlier learned that phi naught is the same in either domain, whether it is the temporal description of the phase function or the spectral description phi of t or phi of omega, because phi naught does not contain, for example, any other factors. It's if you think about it in radians, then it's just has the measure in radians, right. So, for other pulses, however noisy, lousy, whatever we may want to call such spiky pulses, the time bandwidth product would effectively be larger for these kind of pulses, and the point is made that the best TBP, the least, that is best being least in this case, is for pulses which have a very neat profile and very neat phase profile. So, for these spiky pulses, we can again have we can always ask the question, what do you even mean by the width? There are so many spikes involved. Which spike do you prefer? What is the width? So, there we introduce the notion of coherence time, which we will revisit later in terms of pulse metrology, where coherence time is the smallest temporal structure in a pulse that has many different substructures constituting it. The shortest or the narrowest piece in time of this is the coherence time. That coherence time cannot be shorter than 1 over the bandwidth of the pulse, which is delta W. So, delta W is the bandwidth of the pulse. Okay, so, we considered examples of a chirp pulse, that is all fine. Okay, this sets us on to nonlinear optics. So, to say what is nonlinear optics and what are we going to cover in this section of the course, as I said in a nutshell. So, we will look into the physical origin of refractive index, the something that high schoolers start to get introduced to, right. A very sort of obvious, you can say, physical or optical measure, because optics is a very old science, you can say it even predates physics in some sense, but that is just a matter of history if you wish. But the point being that refractive index is one of the most earliest physical quantities that we are taught and learn after perhaps something like mass, length and time. Now, the notion that we have developed in this course particularly is that this very important quantity is a real number, but in learning about media which are absorbent, we discuss the fact that we can turn this into a complex number with a real and imaginary part to keep information very compact and put it in a very sound mathematical formulation and footing. We could turn this into a complex number with a real and imaginary part, where the real part is the refractive index that we are used to, and the imaginary part has to do with absorption. Okay. So, what in this section one of our first goals will be to ask the question, where does this originate from? What makes materials have a finite refractive index? The refractive index of vacuum is 1, is unity. Okay. So, N vacuum is unity, but this is true only at low intensities. Okay. So, we must say at low intensities the refractive index of vacuum is unity. This is also something we have to think carefully about. What if I keep cranking up the intensity of the propagating electromagnetic wave? Will the refractive index forever remain unity? Good question. Next, we will see later on that this also implies isotropy. Isotropy is lack of any preferential direction to refractive properties. So, it is classical vacuum with a low intensity beam, electromagnetic wave propagating through it has a refractive index of 1, and this refractive index is isotropic. It does not depend upon either the direction of propagation or the polarization of the electromagnetic wave propagating through it, but both these are true only at low intensities, strictly true only at low intensities. Okay. At sufficiently high intensities, how high is high? Good question. We are not going to step into answering that, although it is an excellent question to ask that about. At sufficiently high intensities, the refractive index need not be 1, but even more important is vacuum need not even be isotropic. The opposite of need not be isotropic could be birefringent. We will see what this means as things go along. It is essentially even for what we call vacuum, I am not even talking about air, ideal vacuum, right. Both refractive index being unity and being isotropic imply that the medium is linear, isotropic, and we can add to it homogeneous. All these three are implied by saying that the refractive index is unity and the medium is isotropic. At high intensities, it is neither isotropic nor is it unity. At sufficiently, if the lowness of in the intensity domain is lost, this is also lost. So then it's a beautiful physics question to ask. In other words, even for this case of vacuum, if intensities start becoming high, nonlinearities must be considered. Nonlinearities must be considered. Okay. This is not necessarily a scenario where the electromagnetic field is quantized and is thought to constitute of photons. Even for a classic in a semi-classical scenario where the electromagnetic wave is a classical field and vacuum is treated in a sufficiently quantum way, this starts to manifest itself and we need to consider optical nonlinearities. So, why I am making this point is that nonlinearities start to emerge the moment we question the origin of these physical properties at something which is a more ab initio, fundamental or basic level. In other words, we start asking the question of the following question. Okay, let this animation run, we will talk about it soon. When we start asking the question, what is the origin of these physical quantities, parameters, properties. If you are a particle physics enthusiast, your answer to where does mass arise from was answered by the discovery of the Higgs boson. For example, where do atoms get their charge from? It is from the elementary constituents of the atom. So, it is not, we could ask a question fundamentally of a deeper sense. We could peer deeper into matter and ask this question for mass, which is again a very elementary property. The answer turns out to be furthermore complex. In the case of studying these phenomena, we have two entities. We can say this is light and matter interacting with each other, and we have to take the term interaction very seriously. Okay. So, by which we mean two questions. Light matter interaction is about answering the question, what matter does to light propagating through it, it is implied, does to light propagating through it. Likewise, what does light propagating through a medium do to matter contained in the medium. So, matter, light, matter, that is interaction. They are both in a dance, basically they are dancing together essentially. Okay. That is basically the whole idea of this. So, the question that we are asking is, what happens when light interacts with matter, what matter does to light and what light does to matter. When light encounters an atom, a prototypical atom, we can replace this atom with something more complex later. So, but it is easy to envision a so called hydrogen atom, which is the textbook atom, nucleus plus an electron cloud. The electron cloud in this case is thought of as a cloud. If you are an advanced physics student, you have no problem with this picture. You know this from at many levels of complexity, if I may have such a introduce such a notion. But if you aren't, if you are new to some of this physics, this picture of a positively charged nucleus with an electron cloud around it, which is a fairly accurate description of this scenario, is good enough, provided we just simply bring in notions from electrodynamics, which we know very well, wherein we say that when an atom encounters a light wave, it sets the electron cloud into oscillations. So, the light interacts with matter, and while the interaction is still taking place, the electron cloud performed oscillations, okay, because the electromagnetic wave that was incident had an oscillating electric field. So, very simple notion. We will write down even some math for it, but this is the underlying concept, right. So, what happens when this kind of a thing happens? Logically, what would we expect based on known phenomenology? Based on known phenomenology, we would expect that possibly some of this energy is the radiant energy can be absorbed by matter. Okay, why do we know this, or how do we come to this conclusion? Everything gets heated up by light, and it is a day to day experience. So, of course, a part of the beam gets absorbed, but does the complete beam get absorbed? No, otherwise we would not be able to see objects. If everything of light that falls into matter gets absorbed, it would just heat up the material, because energy has to be conserved, and we would have nothing left for things to see. So, if the medium is say transparent or semi transparent such as glass, then a part of it, while being absorbed, another part of it is refracted. We just saw in a couple of view graphs earlier that the absorption was captured in the absorbance which we wrote down, which we gave the symbol alpha to, and refraction was captured in the refractive index. That is why it is the index of refraction or refractive index. It is the particular index, which we early on learn is essentially the ratio of the velocity of light in that given medium versus the ratio of light, the velocity of light in vacuum, okay, again at low intensities. I would add that as a fine text to it. And refractive, the effect of refraction for a beam propagating in a sort of one dimensional scenario amounts to modifying the phase of the beam, which is also what we saw, because n, this factor appeared in the output electromagnetic waves description as E out was a modified amplitude E in times something multiplied by the exponent of I times n omega by c times L. This is the equation we just encountered. So, therefore, refraction modifies the phase, whereas absorption modifies the amplitude of a beam, right. Now, absorption and absorbance alpha and refractive index n are both dependent on frequency. If we now consider a broad source, okay, passing through a gas of atoms, and then we measured the transmission through this gas of atoms, okay, the scenario that we just encountered over here, right. It is one atom here, but we could have had a gas of atoms. We have a radiation which can be sufficiently broad in its spectral content, pass it through and measure the absorption of this radiation as a function of frequency, and give that absorption colors, as is done here in this little reference from which we got this view graph. You essentially see what we call spectral lines. These are special wavelengths of frequencies where light is preferentially absorbed by this gas or group of atoms. By a gas, we mean a group of atoms which ideally is not even interacting among each other.